There's some really interesting applications of a magnetic force on moving charges at this level. Auroras, we've talked about this before in the lessons, a captured cosmic particle by the magnetic field of the Earth will cause radiation to be emitted because of the magnetic force as it gets drawn in by the magnetic field of the Earth. Velocity selector, I have that over here. This is a velocity selector here. When we send it through, only certain velocities get through because we're balancing the magnetic force with an electric force. This is also an example over here is a cathode ray tube, an old style television display or computer monitor has a CRT in it, and that is a velocity selector. Also, a mass spectrometer. If you're in chemistry, this is something you may be familiar with, is how to do identification of elements with a mass spec. And so all of these deal with magnetic fields and magnetic forces on charges. How does that work? So if I shoot a charge into a magnetic field, and you can just see that I have in the picture here, I have a constant velocity and a constant magnetic field. The magnetic field is into the page. If I shoot some charge, and we're going to see that this is a negative Q, so maybe this is an electron, into this constant magnetic field, I would have velocity to the right, the magnetic field into the page, and the force upward on a positive charge, so we see the force downward on a negative charge. So what happens is this force isn't causing the velocity vector to lengthen or get smaller, right? When you look at the definition of acceleration, and I have that over here, the definition of acceleration is the change in the velocity vector over the change in time. And remember that a vector is magnitude and direction. So we can have the magnitude and we can have the direction. So just to review with centripetal acceleration, the magnitude is, we can do this, v final minus v initial over the delta t. And in this situation, we're not changing velocity. This term would be 0. What we're having is that velocity vector, the vector v final minus the vector v initial is changing, right? You can see that if I call this v1 and this v2, the velocity vector is changed. So we're getting a constant force causing a constant acceleration, and what happens is this results in circular motion, and you can see that here. At any point when I put my thumb in the direction of the velocity vector and the magnetic field in the direction of the my fingers, I get the force outward for a positive charge, which means it's inward, and that happens all along. And so you get this charged particle moving in a circle in a constant magnetic field. What we're going to remember is that the centripetal acceleration, A centripetal, we can remember as v squared over r, or we can also remember it's omega squared r for circular motion. And when we apply Newton's second law, right, the net force equals ma, there's the net force, I can say that the net force is the force from the magnetic field, QVB, and we're going to note that the velocity and the magnetic field are perpendicular to one another, so it's sine 90, so there's a 1 in there. So I'm not going to put it the factor of 1, but I will plug in here v squared over r for the centripetal acceleration, right? There's acceleration here. It happens to be centripetal. And so you can see that this equation simplifies, and that's as easy as this is. For a mass spectrometer to have some sort of circular motion to find the mass and identify an element, it just comes from this simple equation. QVB equals mass times centripetal acceleration. And when you solve this equation for r, you can do the algebra on this, but you will see that the equation becomes mv over qb. And so this radius r in the magnetic field, this is the radius r, is related to the initial velocity of that charge moving into the magnetic field, the value of the magnetic field, and that mass, right? That's what the important part for a mass spec is, to know the mass. That's sort of what the mass spec measures, is the mass. You set it up so that there's a constant velocity, you set up the magnetic field, you set up the charge, whether it's single charge or double charge, whatever. And so what you get out of it is the radius. You measure the radius, and that tells the mass. And you can see something with a larger mass is going to have a larger radius. It's going to require a larger acceleration in order to turn it into a circle. If it's moving faster, it will have a larger radius. It just won't turn in a circle as quickly. Also, those values of if it has a larger charge, it's more affected by the magnetic field, and if the magnetic field is larger, it will have a larger effect on that moving charge. So you can see all the variables are there, and that's the application of a mass spectrometer. Often they will ask, what's the distance along here that it would hit? So remember that this distance along here is 2 times the radius, and this equation only has the radius in it. So that's the first example of an application of a magnetic force on a moving charge. The other one is the velocity selector that I mentioned earlier. The velocity selector is a combined effect of simultaneous constant uniform external electric field and magnetic field. That's what we have going on, is an electric field and a magnetic field. And what happens is we set it up so that these two forces balance one another. And we saw that in the example, we had the weight balance the magnetic force. Here we're using an electric field to apply a force. And so we're not worried about the mass here. These two forces are so large compared to the weight, we're not worried about the weight at all here. We balance the electric force with the magnetic force, and what happens is, because the magnetic force depends on the velocity, only the charges that move with that particular velocity are able to get through the electric field. Very interestingly. If they don't move fast enough, the electric field will dominate, and if they move too fast, the magnetic field will dominate, and if they move just right, they will move straight through. So that's the idea. You can see the right-hand rule here. You may be asked to do this in different situations. And what we're going to remember is that the force by an electric field is given by Q. I'll write it out here. F equals QE. This is a vector equation. For an electron, it will move against the field. So that's why I drew it in this direction. The electric force will cause it to move against the electric field. So the magnetic force must be oriented to oppose that, and that's how you get the magnetic field out of the page, is because it would be, the magnetic force would be upward on a positive charge, but it's downward on a negative charge, right? We have an electron in here. So we orient these fields very particularly. We're going to take the two concepts here, the velocity selector and the circular motion for the mass spectrometer, and work them together in a problem. I picked out an example, the mass spectrometer. It says a singly charged ion, 22 AMU atomic mass units, is sent through a velocity selector set with a magnetic field of 0.15 Tesla. The voltage between the plates of the velocity selector is 3,000 volts, 3 kilovolts, and the plates are 1 centimeter apart. Determine the velocity of the ions that emerge from the selector. I'm going to notice also that this is singly charged. A singly charged ion has just the elementary charge, 1 elementary charge on it. Here's the velocity selector over here. We have a positive plate and a negative plate here, so we can see the electric field is pointing in this direction. The electric force is upward and the magnetic force is downward. And we want the velocity. Okay, so in a velocity selector, those two forces are equal to one another. So I'm going to set QE equal to QVB. And we're going to note that the magnetic field and the velocity are perpendicular to one another. So we don't have the sine theta term. That's sine 90, which is 1. And so we get this relationship that the charge cancels on both sides, and we can find the velocity by taking the electric field and dividing by the magnetic field. Keep this equation in mind as we head towards light as well. Velocity selector is a very interesting term for this situation. So I have the magnetic field, but I need the electric field, and they give me voltage and distance. I know voltage equals electric field times distance. So if I want to find the electric field, I would take voltage and divide by the distance. So I get voltage over distance over the magnetic field. And I can plug numbers in for that. The voltage is 3,000. The distance is 0.01 and the magnetic field is 0.15. And when I plug that through a calculator, we get that the velocity is 2 times 10 to the 6th meters per second. So that gives us the velocity. That's part A. B, I kind of touched on a little bit earlier. B asks, is the ion positively or negatively charged? So what we're going to notice, what I noticed right away, is the direction of the electric field. There's the direction of the electric field and the direction of the electric force. And what I see is those are both in the same direction. And remember the equation that I wrote on the previous slide, F equals QE, and this is a vector equation. If the electric field and the electric force are in the same direction, that means the charge had to be positive. So I'm going to say that this is a positively charged ion. When I see this positively charged ion move into this other magnetic field in the mass spectrometer, I'm going to note that the velocity is to the right. The magnetic field is out of the page. My fingers are pointing at me, so I get the force downward. So the direction of the magnetic force over here is downward when it initially enters the field, and then it will be caused to move in a circle as that force reorients and that object experiences uniform circular motion. So that's B, is it's positively charged. C asks, the magnitude of the magnetic field in the second region is 1.5 Tesla. Calculate the distance away from the entry point the ion hits the wall. So we want to find this distance D, and I had mentioned that before on the previous slide. The distance D is 2 times the radius. There's the equation for radius here, and so I'm going to say D equals 2 times the radius, which is 2mv over qb. The mass, we can figure out 22 AMU. If you know how many kilograms are in 1 AMU, that's the simple conversion. We know the velocity. We know the charge is singly charged, and we were given the magnitude of this second magnetic field, 1.5, 10 times bigger. So we're going to go 2 times 22, and then there's 1.66 times 10 to the negative 27th kilograms in an AMU, and the velocity is 2 times 10 to the 6th. I'm going to take all of that and divide by the charge. It's a singly charged ion, 1.6 times 10 to the negative 19th, and the second magnetic field is 1.5. When you run all that through the calculator, you get that distance D to be 1.3695 meters, about 1.4 meters. So if you had a heavier ion, it would go farther. If you had a lighter ion, it would not go as far. And so that's how you can tell the difference. This picture is actually for 2 oxygen ions, the 2 different isotopes of oxygen ions, and that's why you can use a mass spec to figure out isotopes, because the slightly different mass has an effect on this distance that this ion traverses in the magnetic field. And if you know the distance it travels, then you can identify what that mass was and what that ion had to be, and then you know the isotope. So a really cool application of charges moving in a magnetic field.